Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 10, Lesson 1 on polynomial expressions. So we're entering into an entire unit on what are called polynomial functions and rational functions. Rational functions will just be the ratio of two polynomials, and we'll get to those a few lessons down the line. For now, and in this lesson, what we want to do is take a look at polynomial manipulation, the work on polynomials, which you've done a lot of already in this course and in previous courses. So let's jump right in and do some review of some of the things you should already kind of be comfortable with in polynomials. So polynomials. Many of the expressions that you work with in mathematics are known as polynomial, the sum of many monomials. The definition of a polynomial of a single variable, because you can have polynomials of multiple variables, but the definition of a polynomial of a single variable is shown below. Let's take a look at it. A polynomial is any expression of the form a times x to the n plus b times x to the n minus 1 plus c times x to the n minus 2 plus, etc., plus a constant, where the exponents n, n minus 1, n minus 2, etc., are all positive integers, positive whole numbers. Note that not all powers need to occur because the coefficients, i.e. the a, the b, the c, etc., can be equal to 0. They can be 0. So just as a little sort of some examples, right? Polynomials can look all over the place, so here are some examples of polynomials. Here's a very straightforward one. 7x to the fourth plus 2x cubed minus 3x squared plus x minus 5. But, and in that case, you've got all the powers represented, 4, 3, 2, 1, and then a constant. Here, in the second one, negative 4x to the fifth plus 8x minus 4, right? That's still a polynomial, even though we don't have an x to the third and an x squared. We could think of it as negative 4x to the fifth plus 0x to the fourth plus 0x cubed plus 0x squared plus 8x to the first minus 4, right? And we can keep looking at each one of these. The key is in each one of them, right, the powers on the variables are all whole numbers. They're all positive. Now, compare and contrast that, right, with examples of non-polynomials. The first one, 8x squared plus 3x minus 7x to the negative 2. What truly makes that one a non-polynomial is that exponent of negative 2, all right? That means it's not a polynomial. And again, polynomials are kind of like integers, okay? They can't have any fractional parts to them. But x to the minus 2 is 1 over x squared, right? That's a fractional part. It's like a hundredth, if you will. In the second one, 4x to the fifth minus the square root of x plus 9x plus 4, everything there is perfectly good except for the square root of x, because that, as we know, is x to the 1/2 power. And all of the powers in polynomials have to be whole numbers. They all have to be positive whole numbers. The third example, we've got the absolute value of x plus 1 over x squared minus x plus 2. The minus x and the plus 2, those are perfectly good, but the 1 over x squared, that's a problem because that's really x to the minus 2. And that absolute value of x, even if we didn't have the 1 over x to the second, that would make it non-permissible. They can't have any absolute values just randomly thrown in. And our final one is, like a fraction in its entirety. That's what we'll eventually call a rational expression because there's a polynomial on the top, there's a polynomial on the bottom, but overall, that doesn't tend to be a polynomial. All right, so that being said, let's talk about polynomial terminology. All of this you saw in Algebra 1, but we want to review some very basic notions. Exercise number 1. There's a considerable amount of terminology associated with polynomials. We review it in this exercise. Consider the polynomial expression 5x plus 2x squared minus 9 minus 7x cubed. Letter A. Write this polynomial in standard form. So that's our first piece of terminology, the standard form of a polynomial. And what that means is to write it in decreasing order of exponent, all right? One of the things that's very important is make sure the coefficient, along with the sign of the coefficient, comes along with the exponent. So let's do this. Let's write this thing in standard form. And it's pretty easy, but the idea is, right, our first term is negative 7x cubed. Our next term is positive 2x squared. our next term is positive 5x, and our last term is negative 9. So that would be the identical polynomial, but written in standard form. Our exponents are decreasing. Let's talk about letter B. What is the degree of the polynomial? So the most important term in any polynomial is the one that has the highest power, and the degree is simply that power. So the degree of a polynomial is simply its highest power. So we would call this a third degree polynomial. So it's really simple, right? And that's important because that term, the negative 7x cubed, is the absolute most important term of the polynomial. Now, kind of building into that, let's take a look at letter C. What is the leading coefficient of the polynomial? Well, hopefully you know, right, that coefficients are the numbers that are multiplying the variables in any expression. In any expression, the coefficient is the number that's multiplying the variable. The leading coefficient is the number that multiplies the highest powered term. So the leading coefficient in this particular problem, and actually let me erase that, the leading coefficient in this problem is negative 7. All right, and we call it leading because it's literally the first number that we're going to see when we write our polynomial in standard form. All right, so our leading coefficient is equal to negative 7. And finally, letter D. What is the constant term of the polynomial? Well, the constant term of the polynomial is the term that wouldn't change, the term that is constant, wouldn't change if the value of x changes. So the constant term in this polynomial is equal to negative 9. Now, sometimes polynomials, right, will have a constant term of 0, right? If all of the different terms have an x attached to them, then the constant is just 0, because we could think of it as plus 0 on the end. All of these terms are really important. Standard form, degree, leading coefficient, and the constant term. Very, very important before we move on. Let me just change into blue. Try to change into blue, get rid of that. All right, so exercise number 2. For each polynomial below, do the following. Number 1, write it in standard form. Number 2, identify its degree. And number 3, identify its leading coefficient. All right, well, let's do letter A together. These are pretty easy manipulations, but it's again important to go with it. So what do we have for letter A? We've got 18 minus 5x squared plus 3x. So the first thing I want to do is write it in standard form. Easy enough. I'm going to look for the highest powered term, which is negative 5x squared. Then I'm going to go one down from that, plus 3x to the first, and then I have plus 18. So there I've got my polynomial written in standard form, so maybe that's number 1. Number 2, identify its degree. Well, that would be a second degree polynomial because the highest power is 2. And the leading coefficient is the coefficient on that term, which is equal to negative 5, right? So really pretty easy manipulations on all of these. What I'd like you to do now is pause the video briefly, or for however long you need to, and try to do both letter B and letter C. Write them in their standard form, identify their degree, and then identify the leading coefficient. All right, let's go through them. So letter B, I've got x cubed plus 10 minus 6x. All right, so number 1, right, the highest powered term is just sitting there. So it's x cubed. Then I can do minus 6x plus 10. I don't have to put an x squared term in. If you really wanted to put in 0x squared, you could, but the important part is to write it in decreasing order of exponents. This is a third degree polynomial because the highest power is 3. And our leading coefficient is equal to 1, right? I don't want to say my leading coefficient is ever equal to x or x cubed or anything like that. I can think about this as 1x cubed. Okay, so for letter C, right, the first thing I want is in standard form. My highest powered term is that positive 2x to the fourth. Then I have positive 5x cubed. And I have positive 8x squared. And then I have negative 7x. So, right, standard form. This is a fourth degree polynomial since its highest powered term is to the fourth. And the leading coefficient is equal to 2 because it is 2 times x to the fourth. All right, so there we go. And again, very, very important. Very important because ultimately speaking, the degree is going to be very important in terms of how functions based on these polynomial expressions act, and its leading coefficient is also going to be very important in terms of how functions behave. And we'll get into polynomial functions starting in the next lesson. Now, obviously, you want to be able to do operations with polynomials, and you've done stuff like this before. Polynomials are directly analogous to the whole numbers. They can really be thought of as kind of like whole numbers with bases of x instead of bases of 10. They add, they subtract, they multiply, and they even divide, just as whole numbers do. You've done many of these operations in previous units of this course and in previous courses. So let's take a look at exercise number 3 and see if we can do some of these operations. Exercise number 3. If f of x equals 2x squared minus 5x plus 7, and g of x equals x squared minus 3, then find expressions for each of the following. Write all final expressions in standard form. So, letter A asks us to do f of x plus g of x. That'll be pretty simple. Letter B asks us to do f of x minus g of x. A little bit trickier because of the subtraction. And letter C asks us to do f of x times g of x, which is definitely the most complicated of the three. Here's what I'd like you to do. Pause the video right now and see if you can do A and B on your own. We'll go through them. And then maybe we'll go through C together. Pause the video now and see what you get. All right, well, f of x plus g of x, this is simple enough, right? We are just going to do 2x squared minus 5x plus 7 plus x squared minus 3. This is just an issue of combining like terms. We have 2x squared and x squared, which will be 3x squared. Nothing combines with that negative 5x, and 7 minus 3 is positive 4. So f of x plus g of x, 3x squared minus 5x plus 4. Now, as always, subtraction we have to be a little bit more wary about. So I'm going to say this is equal to 2x squared minus 5x plus 7 minus, and of course red just had to come out there, minus x squared minus 3. Here it's important to put that x squared minus 3 in parentheses so that I can remember to distribute that subtraction. Negative x squared plus 3. But now it's just an issue of combining like terms. 2x squared minus x squared is a single x squared. Negative 5x doesn't combine with anything again. And 7 plus 3 gives me positive 10. Okay. Now the last one, f of x times g of x. That's much more complicated because unlike letter A and letter B, right, where we're just really combining like terms, when we multiply two polynomials together, it always becomes a little bit trickier, all right? And in fact, maybe what we'll do is we'll actually kind of come down here to give ourselves some more room, all right? So let me just extend the page. So letter C, we want to do f of x times g of x. And let me just write what those two are down again so that we've got them. We've got f of x equals 2x squared minus 5x plus 7. And g of x is equal to x squared minus 3. So the first thing I might do is I might just write out what this is going to look like. Right? I've got 2x squared minus 5x plus 7 times x squared minus 3. So to begin with, we should just start there. What I'd like you to do is pause the video, take a few minutes, take as long as you need, see if you can work this out, and write your answer again in your final form that's the standard form of a polynomial. And then we'll go through it. All right, lots of good ways to do this. We could use an area model. I'm going to actually use what's called double distribution. In other words, what I'm going to do, after I extend the page a little bit more, is I'm going to first multiply everything by x squared, and then I'm going to multiply everything, well, I shouldn't say everything, I'm going to multiply the first parentheses then by -3. All right, so I multiply that 3-term polynomial by x squared, then I multiply it by -3. And now I can just do distribution. So x squared times 2x squared is 2x to the 4th. X squared times -5x is -5x to the 3rd. And x squared times 7 is positive 7x squared. Got to be careful here. -3 times 2x is -6x squared. -3 times -5 is plus 15x. And -3 times positive 7 is -21. Now typically we would have a ton of different stuff to combine here, but in this particular case the only two terms that combine are the 7x squared minus 6x squared. The 2x to the 4th doesn't combine because there's no other x to the 4ths. Nothing combines with the -5x to the 3rd. 7x squared minus 6x squared is 1x squared, but I'll just write it as x squared. And then nothing combines with the 15x, nor the constant term of -21. So we end up with a polynomial that is a 4th degree polynomial, leading coefficient of 2, constant term of -21, etc. All right, let's do a little bit more work with polynomials. Here we go. Products of polynomials, which is what we just did. Products of polynomials are certainly more challenging than sums and differences. We practiced these in Unit 1 and Unit 7, and in the last exercise. But more work with these products is important. So let's take a look at exercise number 4. Consider the expression x minus 2 times x plus 5 times x minus 7. We could really think about this as the product of 3 exceptionally simple polynomials. Letter A, find this product and express it in standard form. Use an area model to help if needed. All right? So we need to multiply these all out, and let me remind you, just like multiplying numbers, just as if I had said, what is 5 times, I guess, 8 times 2, right? If I asked you to do 5 times 8 times 2, the first thing that you would do is find the product of 2 of those, and it wouldn't matter which, and then take that product and multiply it by the third one. Same thing here. Find the product of any 2 of these binomials and then multiply them by the third binomial, probably using what we did in the last problem. Either way, take a little bit of time and see what you get. All right, well, probably the most natural thing for most people will be to find this product first. So, you might on your paper, you might say, all right, I'm going to do x minus 2 times x plus 5. That would give me x squared plus 5x minus 2x minus 10. And that would be x squared plus 3x minus 10. And now let me remind you, so like in the last case, right, we did that using just double distribution. Let me remind you of how to use an area model to then take this particular trinomial and multiply it by x minus 7, because this is a nice way of just keeping track of things. I could now kind of go something like this. Okay, I'll put x and minus 7 here, and I'll put x squared plus 3x minus 10 here. And now I just kind of fill in the products. X times x squared is x cubed. X times 3x is positive 3x squared. X times negative 10 is negative 10x. Negative 7 times x squared is negative 7x squared. Negative 7 times positive 3x, negative 21x. And negative 7 times negative 10 is positive 70. One of the beautiful things about area models is that oftentimes along the diagonals we have like terms. So this ends up giving me x cubed minus 4x squared minus 31x plus 70. Let me make sure that's correct. And it is, right? Very important to be able to multiply out 3 or more binomials. Now let's take a look at letter B. Given the factored form of the expression, what are the zeros of this polynomial? Verify using a table on your calculator. Okay, so remember, this polynomial and this factored form of it are the same. They're algebraically equivalent. What are the zeros, right? What values of x make that 0? Use the zero product law to very quickly tell me what those are. All right, well, remember the zero product law. Any value of x that makes any one of these factors equal to 0 will make the entire polynomial equal to 0. So x minus 2 equals 0. That gives me x equals 2. X plus 5 is equal to 0. That gives me x equals negative 5. X minus 7 equals 0. That gives me x equals 7. So those should be my 3 zeros. Now, one of the cool things is I can actually use these zeros to check to see if I multiplied that thing out correctly. Let me take a look on my calculator. All right, let me kind of go in and open up a brand new document. All right, I'm going to add a graph, and I'm going to actually put that polynomial in. X to the third minus 4x squared. Oh, that's not what I wanted. Menu. Graph edit, function. I didn't, whoa. Wow, this thing is giving me a hard time right now. Okay, maybe I have to slow down. Go up 1, minus 31x. I know you all love it when my calculator goes rogue on me. I don't love it. Okay, I think that's right. I'm gonna hit enter. All right. You can even see the zeros graphically. Like literally, we have a 0 there at -1, -2, -3, -4, -5. We have a 0 at -5. We have a 0 at 2, and we have a 0 here at 7. But if I go into my table by hitting Control-T, there I can really see my zeros. There's 1 at -5, right? Actually, let me move it over here, right? Because I have zeros at -5. Okay, I can pan down a little bit. Our next one should be at x equals 2. There's a 0 at x equals 2. And I should have a 0 also at x equals 7. And there it is. I love using tables on my calculator to see if I've multiplied out a bunch of binomial factors correctly. Because if I have, right, and I put that final polynomial into my graphing calculator, and I can easily tell the zeros from its factored form, then I can see whether or not this is truly the correct product of those 3 binomials. It's really kind of cool. Plus, it reinforces the connection, it reinforces the connection between the zeros of a polynomial, right, and its factors. A really, really important connection, more important in this unit than anywhere else in the course. All right, now let's take a look at one last thing, and this is an interesting pattern. Because of how terms can combine when products are formed, interesting things can happen, including having some of the terms sum to 0 and leaving you with a very simple polynomial. And you've seen this before, right? Especially when you've had things like, let's say, x minus 3 times x plus 3. When you had something like that, right, then what would happen is you'd have a negative 3x and a positive 3x, right? And you'd get something like x squared minus 3x plus 3x minus 9. Those would cancel, and you'd just be left with x squared minus 9, right? That can actually happen on a much larger scale. So let's take a look at that in exercise number 5. Let's take a look. Consider the products x plus 3 times x squared minus 3x plus 9 and x plus a times x squared minus ax plus a squared. Now, by the way, notice that even though this one's a lot more symbolic, this one has the same structure as this one. In other words, x plus a number equals x squared minus that number times x plus that number squared. That's exactly what this is. X plus some number times x minus the number times x plus that number squared. Something really cool happens here, all right? Why don't you try to find this product when you multiply that by that, see what final product you get. Pause the video now and try to work it out. All right, let's take a look. Well, I've got x times x squared, which gives me x cubed, x times negative 3x, which is negative 3x squared, x times positive 9x, 3 times x squared, which is 3 times x squared, 3 times negative 3x, negative 9x, and 3 times positive 9, positive 27. Now, look at those like terms right along the diagonal. Positive 3x squared, negative 3x squared. Those cancel. Positive 9x, negative 9x. Those cancel. So what do I get? I get x cubed simply plus 27. That's it. X cubed plus 27. And it's remarkable. Here I have a binomial times a trinomial. You know, typically that should give us 6 terms, and it all kind of collapses down to 3 terms. Really, really kind of cool. All right? Now, why don't you go ahead and see what you get when you do x plus a times x squared minus ax plus a squared. Pause the video now and see what you can get there. All right, here we go. Well, this one's a little bit more symbolic. Whoops. But I'll get x times x squared, which is x cubed, x times negative ax, which would be negative ax squared, x times a squared, which would be a squared times x, a times x squared, which would be ax squared, a times negative ax, which would be negative a squared x, and a times a squared, which would be a cubed. And exactly the same thing happens. Positive ax squared, negative ax squared. These two cancel. Negative a squared times x, positive a squared times x. These two cancel, and all I'm left with is x cubed plus a cubed. This is going to form the basis in a future lesson of what we call factoring the sum of perfect cubes. X cubed plus 3 cubed, x cubed plus a cubed. Now, we're going to actually end up a lot of times going backwards. If we recognize this, we can make it into this. Or recognize this, we can make it into that. Here, I want to go in the forward direction. So, exercise number 6, using what you found in exercise 5b, find each of the following products. Letter A, x plus 5, times x squared minus 5x plus 25, well, keep in mind, right, what this really looks like is x plus 5 times x squared minus 5x plus 5 squared, right? This directly fits into the pattern x plus a times x squared minus a times x plus a squared. Kind of hard to see that because it's down here versus up there, but ooh, well, actually, it's kind of hard to see that until I just drag it up there, right? Exactly the same thing. And what does this tell me? This all will end up being x cubed plus 5 cubed. Now, we could work it all the way out. We could certainly like use our area model, work it out, get all of that funkiness, but all of this should be x cubed plus 5 cubed, which is just x cubed plus 125. Now again, that is a very specific pattern though. Do you know what I mean? That is x plus a times x minus a times x plus a squared. Take a look at letter B. Here we have x plus 1 times x squared minus x plus 1. Now again, keep in mind, this actually does fit the same pattern because this is x plus 1 times x squared minus 1 times x plus 1 squared. That is still that exact pattern. So what will that end up being? Pause the video now and see if you can write down the final answer. All right, well, this just ends up being x cubed plus 1 cubed, and that's x cubed plus 1. Now, if you're a little confused about this, don't worry, all right? You're going to work with it a little bit more on the homework, and you're going to work with something called the difference of perfect cubes on the homework as well. And then we're going to look at those patterns a bit more in a future lesson to allow you to have one final type of pattern, or one final type of factoring the sum and difference of perfect cubes. For now, let's just wrap this thing up and talk a little bit about what we saw today. Now, a lot of what we reviewed today on polynomials was stuff you saw before, but it's important. The terminology is important, right? The standard form of a polynomial, the degree of the polynomial, the leading coefficient of the polynomial, very important. All those three things you want to have down pat. And then, of course, you do want to be able to add and subtract polynomials, and the harder operation, multiply them. Now, we didn't divide polynomials today because in general, when you divide two polynomials, just like when you divide two whole numbers, you oftentimes don't get a polynomial, right? And just like when you divide two whole numbers, you oftentimes don't get a whole number, right? When I do 10 divided by 3, I don't get a whole number, right? I get 3 1/3. I get a whole number plus some fractional part. And we will see an analogy to that later on in this unit when we divide two polynomials. Sometimes when we divide two polynomials, we do get another polynomial. But oftentimes we get a polynomial plus some kind of fraction, some kind of remainder portion. But that's later on. Now, we also at the end looked at the sum of perfect cubes, specifically the pattern of x plus a times x squared minus a times x plus a squared. And we saw how when you multiply those together, you just get x cubed plus a cubed. That's a little bit complex, and we'll look at it more in a future lesson. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.